folks, I'm going to walk through another example here of calculating the frequency of the photon that's been given up by a hydrogen atom as the electron moves down in energy level. So in the example that we're going to go over, this electron is going to start at the n equals 3 orbit, and it's going to end up at the n equals 2 orbit, and it's going to give up a photon, right? Because as a rule of thumb, what happens is the electrons, if they absorb photons, they absorb their energy and they move up to higher energy levels. If they give up photons, the electrons are losing energy, they're moving towards lower energy levels. Now, when you write out an energy relationship for an electron, it basically, this doesn't come from graduate level quantum physics. This comes from just basic conservation of how numbers work. If you walk into the grocery store, right, and you've got $20 on you, and you hand 5 to the Red Cross guy, you have $15 left, right? And I can write out a little equation for that says this. So the amount I started with, $20, is equal to the amount I gave up, $5, plus the amount that I still have in my pocket. Okay, so the $20 would equal, that's what I started with, and that equals $5, that's what I gave, plus 15, that's how much I have left. In a similar sense here, this electron is starting in the 3rd orbit. Okay, so its energy, I would call that E3, is equal to the energy it gives up. That's the energy carried away by the photon. I call that EPH for energy of the photon, plus the energy it has left, which is now energy in the 2nd orbit. So here's the relationship here, and it's just like this equation up here. I started with this much energy, I gave this much to the photon, this is how much I'm left with. Just like I started with a $20 bill, I gave 5 away, this is how much I have left. So the energy of the photon is equal to E3 minus E2, the difference between these energy levels. Now I've already went ahead and wrote out these calculations. I'm using the values I already calculated on the right for the energies of the different shells. One thing you got to be careful of, there's lots of minus signs floating around. This is E3 minus E2. But E2 is negative 3.4 EVs. So this becomes essentially 3.4 minus 1.51, and we end up with positive 1.89 EVs for the energy of the photon. So this energy, this photon is going to leave with an energy of 1.89 EVs. Now what I'd like to be able to do is calculate, well, what is the frequency of that photon so that I can compare it to the electromagnetic spectrum and see what classification it is. So in order to do that, the relationship is given right here. Energy for a photon is equal to h times f. H is Planck's constant, but again, just like in the last example, Planck's constant has units of joule seconds. So before we can use that relationship in Planck's constant, this energy needs to be converted to joules. So here's the conversion, 1.89 EVs times, notice my conversion factor has joules up top, EVs on the bottom, so these cancel just like every other conversion factor we've done since the first week of this course. Okay. There's 1.6 times 10 to the minus 19th joules per EV. So when we do the multiplication, I got 3.02 times 10 to the negative 19th joules. So that's the energy of this photon in joules. All right, so I come over here now and I say, all right, I want to calculate the frequency. So I solve this for the frequency. It would equal the energy divided by h, Planck's constant. I put in the value, 6.024 times 10 to the minus 19th joules. I put in Planck's constant, 6.63 times 10 to the minus 34th. Hopefully I did this right. I got 4.6 times 10 to the negative, oops, not negative, 10 to the positive 14th hertz is what I get out of this. Okay. Now, if you look up on the electromagnetic spectrum, 10 to the 14th hertz is right around the upper end of the infrared region. So that photon would be infrared. We couldn't see that with our eyes. Now, some important properties here that are extremely important to understand. In the previous example, I worked through the transition going from 2 to 1, and out came a higher energy photon, a UV photon, a photon that came out in the ultraviolet region. That's because the energy difference between 1 and 2 is bigger than between 2 and 3. And as you get further out, the energy gaps get less and less and less. If I calculated the energy difference between a 4 to 3, I'm sure you know this number is going to be smaller, the frequency is going to be smaller, and we're going to get something lower on the spectrum, maybe lower than kind of the bottom of the infrared region, or maybe even out of the infrared region entirely. Okay? If we use bigger gaps, for example, if I did 1 3 to 1, I'm sorry. If this electron started at n equals 3, landed at n equals 1, the energy of the photon will be larger. When I convert it to joules, again, that energy will still be larger. When we calculate the frequency, we're going to get a larger value. So we'll probably get something in the upper UV region, or maybe even doubtful in the X-ray region, no, but probably in the UV region again. So basically, as a rule of thumb, the larger the energy jump, the higher the frequency of the photon will be given up. Okay? And then the smaller the energy jump, the shorter the frequency. I'm sorry, the smaller the frequency will be.